Hello my students, your physics teacher Hassan Darwish with you. You remember in the previous videos I taught you how to study the charging of a capacitor. And in this video I am going to teach you or to study the discharging of a capacitor. Let's start. This is our circuit. We have DC generator here, negligible internal resistance, and when we wanted to study the charging of this capacitor, we just closed K1, switch K1. Clear? Now we are going to study the discharging of the capacitor. So what do? C is fully charged. We open K1 and then close K2. Okay? So when you do this, you have eliminated this part. Why? Because K1 is opened, so the battery is separated, and K2 is closed. So you have eliminated practically this part. But remember, your capacitor is full of charge. Here we have the positive charge, and here we have the negative charge. Clear? Remember. So we start studying it. Clear? Okay. So what's the objective? To determine how the charge or the voltage UC or UMB and the current in the circuit vary with time. Notice here, this is the positive charge on the capacitor and this is the negative charge. Means point M is at higher voltage, higher potential, and B is at lower potential. The electric current always passes from higher potential to lower potential. So this is the sense of current. Notice also that I have chosen the positive sense in the same sense of the electric current. Okay? So in order to know how Q and I are the same, UC and UR, since they are proportional, vary with time, we have to find the function. You have to find the shape of the function here, the shape of the function here. To do so, we start with the law of addition of voltage, right? Okay. So in the law of addition of voltage, notice here UAB equal UAM plus UMB, right? So UAB equal UAM plus UMB. But be careful here. UAB, here is UAB. There is what here? There is a closed switch. Means we have a connecting wire. Now what is the voltage of the connecting wire? Yes, 0. So this is 0 equal. Look at the points A and M. What do we have between A and M? We have the resistor, right? So Ohm's law for the resistor is what? Ri. Good. This is R and this is I. Good. But notice here, you apply Ohm's law from A to M. A to M, opposite to the sense of current. Means we have minus Ri, right? Good. Plus UMB, this is M and this is B, so this is Q because M has a positive charge. Q over C, right? So far we haven't obtained the differential equation because we have two functions here, I and Q. We need only one function, either in I or in Q. So is there a relation between I and Q? You know from the previous videos, yes. Now, I equal derivative of the charge, right? Here it is. I derivative of the charge, Q prime. But here I have added minus. Why? Because I must be positive. Look here, I has the same sense as a positive sense. So I is positive. And since the capacitor is discharging, means the charge decreases. I mean the function decreases. When the function decreases, its derivative is negative. So here, Q prime negative times negative, we get I positive. And I equal minus Q prime or minus C U prime of the capacitor. So replace I here. What do we get? If you put I here, then we have what? Sorry here. Then we have R Q prime plus R Q prime plus Q over C equals 0, right? Or you can write it in an elegant way, Q prime plus 1 over RC Q, this is the function, equal 0. And here we obtain the first order differential equation in Q. Clear? Now what is the solution of this equation? This is called first order because we have first derivative. So first order differential equation in Q. Now what is the solution of this equation? The solution, you are not responsible, as I said in the previous videos, not responsible for the solution. It's always given in the official exams or in an exam. So Q equal Q exponential minus T over tau. And you know, Q, which is the total charge or the initial charge on the capacitor, is CE. And tau equal RC is called the time constant. I verified this in the previous videos. Okay? Now, what is the electric current in the circuit? Let's find the electric current. The electric current in the circuit or in C, the same. Circuit is, you know, I equal minus Q prime, right? Just make derivative here. I equal minus Q prime equal, if you do the derivative, then E over R exponential minus T over tau. The same as the current in the charging case. Okay? So let's do a remark now. Important remark. In this important remark, I'm going to find at t equal to 0, let me use black color, at t equal to 0, you replace in the function, or it is given, q0 equal q, verify this, and I0 equal E over R, maximum. So the charge is maximum and the current is maximum. The second remark, at T equal tau, we also verified this calculation. I can get the charge Q1 equal 0.37. I will leave it to prove this. I will leave it for you. 0.37 Q and I equal 0.37. The initial current means opposite to the case of charging here. At T equal 1 tau, I mean after a time constant tau, the charges dropped by 63%, means the remaining is 37%. 0.3 at T equal 5 tau, practically you can verify that the Q approximately 0 because exponential minus 5 0 and I approximately 0. So in the case of discharging, C practically completely discharged, means it is empty again. Okay, so let's see how the charge, the graph of the charge and of the electric current. Okay, 0.4 graphs of Q and I. Let us first start with the graph of Q. So here is Q. I will use this color, red. At T equal to 0, the charge is Q, right? Total charge. At T equal 1 tau, the charge reaches 0.37. This is 25, 50, 75, 100. 0.37 is here almost. So the curve passes through this point. At T equal to 5 tau, it is practically 0. Now if you draw the curve, it is exponentially decreasing, right? Good. Now let's see the graph of current. The same. At T equal to 0, the current is maximum, E over R, right? The same is if you say UR, because they are proportional, U equal RI. Similarly here, the same if you say UC, because it's proportional to Q, Q equals CU. At T equal 1 tau, it is 0.37. Here it is. 5 tau, the current practically 0. So decreases exponentially. Clear? This is a true one. Okay, you can erase this part. Sorry. I want you to verify that the tangent to the curve at the origin in the same way as cuts the horizontal asymptote at point of abscissa tau. This is the tangent. Sorry, this is the tangent at the origin.